Right. So today we're going to conclude our discussion of chapter 3 in the textbook on problems in elasticity. And if there's time at the end, hopefully there will be, we'll have a chance to maybe review the homework assignment and just make sure that we've covered everything in sufficient detail, or to give you an opportunity to ask questions. But today, again, it'll be a focus on finalizing some of the topics we started last lecture on Tuesday in talking about stress concentrations. And we'll, revisit the same problem that we did last time and think about, well, when is that situation really going to happen? Can you ever really have a concentrated load, for example, applied to some structure? Is that even physical? And if it's not physical, is there some way that we can modify the problem to be more representative of the physical reality? And to do that, rather than considering concentrated point loads, we really do have to take that single concentrated load and distribute it out over some finite area. And one way to do that is through this theory of what happens when two bodies come into contact. So we'll talk a little bit about contact stress distributions, and we'll talk also about stress concentration factors and what do you do when you do have maybe not necessarily a point load applied to a body, but if you have localized features such as a hole in some large object, what happens to the distribution of stresses in the local vicinity of some feature or deviation from a perfect, homogeneous geometry. So, like I said, first thing we'll do is recap on this problem that we solved last time using polar coordinates and using the Airy stress function to come up with the exact solution for what happens to a thin plate. Don't imagine that this domain is necessarily a infinite medium and that we're looking at in cross section maybe a slice through the earth, and that these represent maybe, I don't know, stresses immediately underneath this point of load in the soil. This is really just an idealization of a thin plate subjected to a concentrated load on its boundary. These solutions pertain to that situation. So we can represent the solution in terms of polar coordinates, in terms of stress components, reflecting that polar coordinate frame. So radial stresses and circumferential stresses, but that's a little bit awkward, especially if we really want to know things like, well, what's the stress distribution relative to our usual Cartesian coordinate frame? So you can take that solution, transform it into these Cartesian components simply by applying our usual stress transformation equations to go from one coordinate frame to another. And we get some distribution of stresses that look like this, expressed in terms of the usual sigma xx, sigma yy, and sigma xy components. And we looked at, well, what are some interesting features of this resulting solution? Assuming we have our point load applied right at this red dot, as shown on these three different figures, we can visualize what are the stress distributions in basically the xx stress, assuming x is actually oriented in an unusual way, pointing down into this median. So think of x basically measuring the downward kind of depth, and y is really the horizontal distance relative to the surface. So y is going to, in this case, your right, and x is going straight down. Just a little bit of a clarification there, because usually if I think of XY coordinates frames, I think X goes this way, Y goes up. In any case, we saw that, the stress in each one of these different components of stress will zoom off to infinity at the point of application of the load. And if we look at what happens at increasing levels of distance from this load, clearly that concentrated stress starts to spread out and get distributed throughout the plate until far enough away from that point of application of the load, it almost looks like nothing's happening. But sort of an interesting scenario. And obviously, it can never really happen in real life, because we can never truly apply a concentrated load like this. And so, we can't really believe what's happening in the local vicinity of this point load. We kind of have to say, well, in reality, it's going to be distributed over some finite width. So the stresses truly will not be infinite. That doesn't make any sense. Even though the theory of elasticity gives us the tools to be able to come up with solutions like this, sometimes they're not always reflective of the physical reality. And that's really the takeaway that I want you to have from this problem. There are technically two issues with the fact that the stress goes off to infinity in this problem. And the first is precisely the manner in which we've defined these loads by assuming that they are truly concentrated at a singular point. But there's another issue, and I'll invite you to speculate and kind of put your suggestions as to what you think that other issue is in this context. It has to do with one of the assumptions we made in coming up with this whole theory of elasticity. So I'll invite you to speculate. What do you think might have been an error in our conception of the theory of elasticity that might lead to, bizarre solutions that include infinite stresses? What do you think might be wrong with some of our assumptions?
Is there like a defined boundary?
In terms of this problem, whether we define, let's say, the boundary conditions in kind of like an unusual way, or, was there something wrong in the way that we set up the problem in saying that this was sort of a semi-infinite plate, I guess, that could be, we don't know exactly where its boundary is on these exterior edges. Really, I'm showing just a small square cut out from this semi-infinite plate, but really you can imagine these different boundaries go, infinitely in all directions. It's just this one free surface. In fact, it's not so much that that's the problem, although that is also kind of a fictitious construction. It's a good thing that you point out, because really, when can you ever have a semi-infinite medium? I mean, I guess the universe is speculatively infinite. We don't really know its overall dimensions or whether it has some kind of boundary to it. But in general, it's kind of hard to conceive of, in practical circumstances, a truly infinite medium. So that's a little bit unusual. It's kind of a departure from reality. But in fact, it doesn't necessarily influence the local character of the solution at this point. Even if we had made this plate, let's say, of finite dimension, it doesn't really matter. We'd still get a solution here that would have an infinite stress. So maybe is there something else? And I'll kind of reflect on the different aspects of the theory of elasticity. We should really kind of like break it down and maybe make sure that each of the different components that we've put together, these three primary constituents, compatibility, constitutive law, and equilibrium, and examine each of those and really say, was there a false assumption that we made somewhere along that line of putting all these different relationships together? Was there a false assumption we made that kind of makes this seem rather unphysical? So let's go down the list. What do you think about compatibility? Is there any kind of reason to suspect that compatibility or the strain displacement relationships, might be causing this? I'm seeing some maybe like faint shaking of heads, like probably not. It's kind of hard to think about it. Basically the only assumptions that we've made in coming up with that strain displacement relationship, if you recall, the strain displacement relationship that we derived, which is also equivalently, if we're assuming that the strain field comes directly from this relationship, then we automatically satisfy compatibility, is this. So recall the strain field is just the symmetric part of the displacement gradient. But it turned out that this was kind of an approximation. This was a specialized result that only applied in the case of small displacements or small deformation. Could that assumption maybe have contributed to this scenario? We're really being critical here and reevaluating everything that we know. Do you think that this might be the problem? You say no. Why do you think it's why no?
Because we derive that.
Yeah, I mean, it's kind of hard to see why. I mean, in this particular circumstance, it's hard to imagine why assuming small displacements maybe would somehow lead to an infinite stress. I mean, if anything, I would think If we assume small displacements, maybe the stresses should also be equally small or something like that. Really, this assumption only becomes invalid when we have solutions where, the deformation of this body might include very large rotations or very large amounts of stretching. And certainly if you have a very high stress in this local vicinity, then maybe you do have some relatively large deformations there, but it doesn't necessarily explain why the stresses would go off to infinity. Okay, that's fair. What about, I'll jump to equilibrium. The equilibrium equations, the statement of, the sum of forces and the sum of moments acting on some small chunk of the body, anywhere in the body, have to be equal to zero. Is somehow equilibrium wrong? Was there any doubt about equilibrium?
Maybe we didn't account for damping.
Damping, there might be other basically sources of forces, like maybe there's the self-weight, we kind of neglected that. There's, maybe there's, I don't know, there could even be some kind of external fluid pressure acting on this boundary, like atmospheric pressure or something that's distributed over the sides of this and maybe the exterior faces. There's a bunch of approximations that we've made in simplifying the problem to get it into this format, including various other types of forces, time dependence in how we apply the loading, how quickly we apply it, dynamic effects as we kind of apply it, and then maybe stress waves would otherwise propagate through. We're assuming everything is quasi-static, so there's no time dependence. But really, even if we say, well, those are all approximations, equilibrium is equilibrium. If eventually you allow the time-dependent components of the solution to damp out and go away, then it's sort of like eventually at the end of the day, you'll get something like this, the time infinity solution or the quasi-static approximation. And in general, we kind of say that that's fine. Equilibrium is equilibrium. Newton wasn't wrong. He came up with these equations and they've stood the test of time. So truly, equilibrium is not the problem. So we've ruled out compatibility or the strain displacement relationship is the problem. Equilibrium, if equilibrium wasn't satisfied, then our fundamental understanding of physics is flawed. So I feel like we should keep that one around. The only remaining suspect that we haven't ruled out yet is the constitutive law, or the relationship between strain and stress. Now, I'll give a moment to think about this. We've kind of assumed something pretty critical about the relationship between stress and strain, that it's linear, that if you have, let's say, some relationship that looks like this, then this solution implies that for any possibly even arbitrarily large value of strain, you'll get still a linearly proportional value of stress, let's say in just the uniaxial case, that maintains this same linear proportionality as you increase the loading. So it doesn't actually matter how big you make the stresses or correspondingly how big you make the strains, but this is a big assumption. And this assumption ultimately breaks down, obviously, if we have a situation where the stresses become infinite, because we know, and this really is a good segue into what we'll discuss in chapter 4. We know that really a lot of conventional materials cannot sustain an infinite stress. At a certain point, they'll reach some kind of critical failure stress. And beyond that point, either the material will fracture and fail, and it won't be able to sustain any stresses after that, or maybe it'll start to yield and permanently deform. But it'll certainly never be able to achieve an infinite state of stress. So clearly, the problem with this solution, because the fact that we're getting infinite stresses is partly a consequence of our assumption of linear elastic constitutive behavior, that the relationship between stress and strain maintains this linear proportionality, regardless of how big the stresses or strains are. But in point of fact, that's only applicable up to the limit at which the material can maintain this linear relationship between stress and strain. If you otherwise exceed some critical value of stress, then you really can't believe anything that's happening in that region. So anywhere in this domain where the stresses would otherwise exceed some kind of critical failure stress otherwise, we can safely say that that's just not physical. And you'll see various other solutions, including some very important solutions, like in the case of fracture mechanics, where you want to know what's the distribution of stresses in the local vicinity of some crack tip. And there too, the solution ends up being, infinite, or you have infinite stresses in the local vicinity of a crack tip. But that's simply not possible. Even though that's kind of like very useful to, have, ultimately it's still unphysical because it hinges on this assumption of linear elastic constitutive behavior. So just kind of remember that really the theory of elasticity has its limits. And it happens to be, primarily when materials no longer behave elastically. So just bear that in mind. Elasticity only applies to material behavior that is strictly linear elastic. If we wanted to include other kind of interesting effects with nonlinear material behavior, we'd have to do something different. Our elasticity solutions are no longer applicable in those domains. All right, just remember that. All right, so to help you out with a little bit of the homework assignment, I wanted to at least give some perspective as to how you might generalize this solution that we've obtained for some point load or concentrated load applied on the boundary of a plate, and how you might extend it to determine solutions, maybe with this point load shifted by some arbitrary distance, we'll call it y bar. If you wanted to find out what's the distribution of the stresses, the same solution that we had for the stresses from the previous slide, but we just wanted to know what would the stress distribution look like if the load was over here, then all you have to do is, just modify the location at which you're evaluating this y coordinate by shifting it by y bar. So any expressions that had this dependence on y previously, when p was directly over the origin of the coordinate frame, now you just replace anything that depended on y with this, let's say, y prime, which is just y minus y bar. So shift the coordinate frame by that. Okay. And what's even more interesting is if we wanted to, we could also, let's say, take that single point load and suppose what would happen if instead of applying it at a single concentrated point, what if we maybe distributed it over, who knows how exactly we're going to distribute it, but we could break it up and then treat it as not necessarily a concentrated force per unit of depth, but basically a pressure applied to the edge of this plate. And in doing that, we can, basically get around that problem of having this concentrated load that would otherwise result in infinite stresses directly under the point. If we choose to instead distribute it over a finite width, now we don't have that problem. The stress distribution underneath this load should no longer be infinite. The stress, in fact, should be just proportional to whatever externally applied pressure we have directly under this distributed load. So that's kind of one way that you can maybe avoid this problem and fix that solution so that it's not necessarily, telling you that you have infinite stresses. It's not particularly useful for design purposes if you want to know what's the bearing capacity of some soil underneath a building where you're trying to take that building load and distribute it over the footprint of the foundation of the structure. So instead, you have to kind of take that solution, but by the principle of superposition, it actually becomes rather trivial to just say that the resulting solution to this problem, with now maybe some variable distributed load, is really just the superposition of the solution involving just individual point loads, but summed up over, all the different contributions of maybe this little chunk of point load and this little chunk of point load, each one varying as a function of its offset position y bar. And we can sum together all those contributions, and through superposition, we can then figure out what's the resulting stress distribution, which is kind of a combination of all of the different stresses that would result from, a bunch of point loads distributed over some area, all summed together. In kind of the continuous limit of doing that summation, you get an integral. So that's precisely what one of the homework problems is asking you to do. It's asking you to take the original solution for this kind of point load applied to this boundary. And then instead of treating P as a distributed load, or rather a distributed load per unit depth. They say treat it instead as a pressure, and then integrate contributions from each of these different things to get some resulting stress distribution. They express it in a slightly different format. I'm expressing everything in terms of X and Y coordinates, but for the purpose of the homework problem, I think you'd probably be better off integrating expressions that don't depend on X and Y, but rather which depend on R and theta, if you can get it into that format. Or maybe at least dependence on theta and maybe some other coordinate. The book has some suggested references for which specific equations you should use. But yeah, if you try to integrate these expressions, it'll involve some dependence on y prime that has this dependence on y bar. But it's really important to recognize that the limits of integration and the integration variable for each of these expressions is not necessarily y, the actual coordinate y, but rather the shifted coordinate y bar. That's the thing that p actually depends on. So setting up those integrals is going to require maybe a little bit of careful thinking in terms of how you actually set these up. This gives you at least a reference of how you might do that. But for the homework problem, I can't give it all away. So use this as a guide to figure out that you have to integrate these limits of integration with respect to some kind of shifted coordinate. In the case of integrating with respect to angle or theta, it's kind of a shifted angle, theta bar. And then you can carry out these integrals and hopefully figure out what the resulting stress distribution should be. Quite useful if you wanted to know, what's the actual stress underneath this point. But again, I want to emphasize that this solution only applies to an infinite plate subjected to some distributed loading. And there's limited opportunities where that's really going to be applicable or useful. Maybe in, analyzing what's happening locally underneath the edge of some kind of loaded plate or a beam that could be idealized as a plate. But who here has maybe taken, some kind of geomechanics class or geotechnical engineering class? Or maybe also, is anybody doing kind of research in geomechanics? I don't know, just as well. I'll ask this then. Have you ever had to, for the purpose of maybe designing a foundation, have you ever had to figure out what's the stress underneath the soil of a building or something? Yeah. Basically, you want to know what's the distribution of stresses in the soil so that you're not going to incur some kind of failure underneath the structure in the soil. So how did you do that? How did you determine what's the stress at any point underneath some kind of building footprint that's loaded over some planar area?
Multiplied by the depth. So the vertical stress.
So yeah, in general, I think there's a couple different ways you could do it, right? There's this kind of assumption that if, let's say you had a truly three-dimensional problem rather than a two-dimensional plane problem where we're looking at a plate. Now imagine that this is just kind of viewed in profile, an actual three-dimensional domain. And this is kind of below this line is the interior of the earth or the soil. And maybe you have a building sitting on top of this. And you can idealize the distribution of load applied over the footprint of this building. And say again what you just said, given this.
So the stress is depending on the distance from, or the depth actually, where you are. So Z, and the density or specific graph, no, how do you call that? The gamma of.
Yeah. Assuming that maybe the soil itself has some self-weight, and so technically speaking, as you go further and further down, any soil above this kind of particular line is going to include not just the contributions from this, building load, but also all the self-weight of the soil that lies above that point or above this line. And in general, we kind of have an idea of what this should look like. Take a look at this image. We know that local to the point of application of some load, you're going to have very concentrated forces. But, as you kind of go further and further away from the load, things start to fan out or distribute out. So in reality, these loads, whatever they are coming from the building, they're not going to go straight down, obviously. According to this solution, they should really fan out and they should do something like this, right? Kind of makes sense. So if you wanted to approximate what's the actual stress that gets distributed at some depth below the surface, it's really going to distribute out from this upper point. That's a pretty quick and dirty and approximate way to come up with these solutions for estimating what's the bearing or the stress acting on some kind of plane underneath a building. But it's also possible to come up with solutions in a rather general way to a very analogous problem to this plate problem that we posed. Rather than considering some thin plate that's subjected to maybe a concentrated point load on its edge, now consider this full three-dimensional medium. It's now in 3 dimensions, and we'll kind of define the coordinate system again in this funny way, where maybe the x and y directions lie along the planar surface of the Earth. And let's just define z, going straight down towards the center of the Earth. We can come up with solutions to this elasticity problem in kind of a similar way that we did for the case of plane stress in the 2-dimensional case. It's very similar. It involves also finding solutions to this problem, not in cylindrical polar coordinates, but in spherical coordinates, for which we can also come up with an equivalent Airy stress function and do all those nice things. We're not going to do that because it's, I don't think it's necessarily useful to go through that exercise. But it is useful to know that you can come up with an exact analytical solution for what the resulting stress distribution will be. And it'll look very much like that 2-dimensional plane stress solution, except it'll be now in this 3-dimensional domain, where you can kind of imagine that underneath this point, the stress will fan out in sort of like a circular radius almost as you move further and further down through the Earth. And if you neglect things like the self-weight of the soil and other contributions to the overall stress, you can then figure out what's the stress, let's say at some point, measured maybe some horizontal distance away from the point of application of load and maybe some depth z down into the Earth. You can then measure what's the overall state of stress, its different components at that corresponding location. So it gives you a slightly more detailed description of what the full stress distribution will look like at any point underneath, some infinite medium with a concentrated load applied to it. And you can go through, again, this same exercise of treating that point load as basically just maybe breaking it up into small contributions, distributing it over some kind of finite area. And instead of treating it as a point load, taking this solution and summing up contributions from, point loads distributed over the footprint of some building that you're interested in. And people have done this, and it's actually quite useful from a geotechnical engineering perspective to, do this for maybe complex building footprints or, doing things that include maybe even concentrated loads from localized forces due to columns or other things acting at localized points on the surface. And you can sum all these contributions together using this elasticity solution to get a slightly more high fidelity solution for what the stresses should be at some chosen point below the surface. The guy who came up with this was named Busanesque, and it's basically just a generalized solution of that kind of 2-dimensional plane stress problem. And it allows you to come up with these different stress distributions and figure out not just what's the vertical stress, the ZZ stress, basically the stress acting on the top face of one of these kind of like blocks as you go down, but it also includes some solution for the other components of stress that might act on this block located at some distance here. So particularly in the case of soils, you're really interested in not just like how much, compressive stress can the soil sustain. Well, that's definitely useful to know, but it's not the whole story. And especially if you're trying to design for the bearing capacity of a soil, you kind of also have some other modes of failure. What's a particular mode of failure that you're concerned about when it comes to assessing the bearing capacity of soil? Shear. Yeah, in general, the failure mode for a lot of these bearing capacity problems is not so much the compressive load, the sigma ZC stress, it's more so actually the shear stress. And really, if you want to assess at what point will there be some kind of shear failure in the soil, then you kind of need to know not just the one vertical component of stress, but all these different components. So the Bose-Ness solution gives you a way of determining that. And we'll talk in more detail about specific ways of assessing, well, at what point will this local chunk of material undergo some shear failure? In general, it'll depend on, yes, the amount of shear load that's being applied to this small chunk of material, but it'll also depend on things like how much is that chunk of material being compressed. So it's actually a pressure-dependent shear failure mode. That's probably something that if you've taken a class in geomechanics or geotechnical engineering, you're probably well aware of things like Moore-Coulomb failure criteria, which is basically a combined statement that, the amount of shear load that a chunk of material, especially like a soil or some other kind of granular media, can sustain is dependent on how much pressure you're putting on it. So the more pressure you have on some kind of piece of granular material like a soil, the more shear load it can sustain. And we'll examine exactly how that manifests as a three-dimensional failure criterion on the stress in chapter 4. All right, just to give you some perspective on that and how it relates back to geotechnical engineering and other interesting applications of this theory. Okay, now let's dive into more of the structures domain. We talked about geotechnical engineering. Let's go back to the structures domain. So in particular, let's look at not necessarily what happens when you have external load conditions that are concentrated on the boundary of the domain. Maybe we have some nice looking geometry and nice looking distributed loads applied to its boundary. For example, let's just take this infinite plate, assume that the thickness of this plate is relatively small, so we can use our plane stress solution procedures and our elasticity solutions developed under plane stress conditions. And let's also just say that this plate is relatively big. So even though it's shown here with some finite size, let's imagine that this plate is actually almost infinite in all these different directions. At least large relative to some local feature, like a hole or some other kind of cutout that's located somewhere in the center of the plate. So the distance away from the edges towards this hole and the radius of this hole relative to the size of the plate are going to be really small. Okay, having said that, what we want to know is if I have some plate and maybe, I don't know, for some reason, I wanted to go to like a bridge girder or some other kind of structural component. And I said, I want to drill a hole right here through the structure. I know it's already sustaining some loads. Maybe it's, subjected to some uniaxial state of tension. Far away from the hole, the load can be idealized as roughly constant under, uniaxial stress conditions. What's going to happen if I drill this hole? Is there going to be a problem? Should I not drill the hole? How big of a hole can I make? Other questions like this are things that you might try to answer if you're trying to, I don't know, drill a hole to allow some kind of appurtenance to go through there. Or maybe you want to put a bolt through it. Or maybe you're trying to do some kind of retrofit. It's good to know, well, am I going to cause any problems by introducing this hole? And to really assess that, we need to know what is the distribution of stress that would happen if we kind of introduce this local defect or local modification to the geometry in a member that would otherwise have seen basically just a constant state of stress, a constant state of uniaxial tension. So if the hole was not there, then the solution to this problem is very easy. It's just, the same uniaxial tension throughout the whole thing, assuming no other kind of components of stress in any other directions. So really what we want to find is the solution for this elasticity problem in the local vicinity of the hole so that we can figure out, do the stresses deviate significantly from that, average or homogeneous state of stress. And the way that we do that is, again, by using our Airy stress function, we can come up with solutions to this problem. Again, I'm not going to go through the steps of actually coming up with the solution to this, in part because it actually ends up being a much more complicated solution than even the previous problem that we considered. But it is still useful to take a look at the solution, and maybe we can surmise some major takeaways. We can come up with a conclusion of how does the stress field locally change in the vicinity of this hole. So just to give you broad strokes what the solution procedure would look like if you had to do it, not that you would. But the idea is we would use our polar coordinate form of our equations of elasticity. So rather than doing everything in terms of Cartesian coordinates with equilibrium and everything defined relative to an XY coordinate frame, it actually ends up being convenient for the sake of this problem, if you have a truly circular hole cut into this member, to do everything in terms of polar coordinates. And what's even more interesting is that when you're solving these elasticity problems, plane stress or plane strain, either one being 2D, when you're solving these equations using the Airy stress function concept to pose some supposed function that generates what the resulting stress component should be, it turns out that there's a general solution for what the Airy stress function should look like using some limited subset of functions. So you don't have to guess the full suite of all possible expressions to represent the Airy stress function. You can imagine, it could be a very long list of different functions. You could say, well, maybe let's look at, functions of R and functions of R squared and functions of R to the third and so forth. And maybe there's other types of functions that you might be interested in. Maybe, I don't know, the exponential of R or the logarithm of R. And there's so many different functions that you could look at. You'd basically exhaust all your time just testing for a given problem, which of these different functions might satisfy the boundary conditions and satisfy compatibility and do all these other things. And people have spent a long time trying to come up with these problems or come up with solutions to these problems. But one clever guy, Mitchell, came up with the fact that for any plane stress problem expressed in polar coordinate form, there is a truly general solution which satisfies compatibility automatically. So you don't have to check the compatibility condition. The only thing that you have to enforce are boundary conditions. So you do still need to enforce boundary conditions, but otherwise it limits the potential solutions for the Airy stress function to kind of like a small subset of possible functions that will automatically satisfy all the other conditions automatically. And that's pretty cool. So really, a lot of methods for solving these plane stress problems in polar coordinates especially boils down to taking the work that this guy, Mitchell, came up with to determine what's the general solution. And it involves basically a summation of terms that involve these specific functional forms. Maybe there's the natural logarithm of R, there's R squared, there's, R squared times the natural logarithm of R and other terms, plus some dependence of maybe some of those terms multiplied by things like cosines of theta in different integer numbers. So composing solutions from this bucket of functions as the potential solution that automatically satisfies compatibility really simplifies the amount of work that you have to do. All you have to do is figure out what are the associated coefficients, let's say, that pre-multiply each of these different individual functional terms such that they satisfy our defined boundary conditions for the specific problem of interest. So really, the solution is always going to look something kind of like this, plus some other terms that I'm not showing here. But it'll look something like that. And the only difference will be that these function coefficients have to be selected such that we satisfy whatever boundary conditions we're imposing on this specific problem. So the solution always looks like that. The only difference is what the coefficients look like. It's kind of interesting. It's kind of cool. But ultimately, you can go through that exercise, assuming you can come up with what the boundary conditions for this problem look like, which, kind of requires you to think about it in terms of, not necessarily what's just happening at the boundary of this interior hole, but also what's happening on the boundary of the plate far enough away, which is kind of equivalent to saying what happens if you take the radial coordinate relative to some center of the plate and look at what happens as r goes off to infinity. That's kind of how you have to enforce these so-called far field boundary conditions. If we suppose that the size of the plate is really big, what we want to know is, at r goes off to infinity, at theta equals 0, I want to have, the axial stress be equal to sigma naught, and there to be no shear stress on this face. Same thing on this top face. As r goes off to infinity, but at theta equals pi over 2, I want to have 0 stress on that kind of top face. And that's more or less how you would go about evaluating these functions and enforcing those boundary conditions. Set r equals infinity, which in the case of, r showing up on the bottom here, basically means that any terms that depend on 1 over r or 1 over r squared, when you plug in infinity, they just go away. And you can use those conditions then to enforce your boundary conditions, the far field stress conditions. All right, so one thing I will also point out was rather unfortunate. If you saw this solution, it does appear in the textbook. They do present this particular problem, but it's wrong. They have a typo. I think it's in this expression for the sigma theta theta stress, as well as I think also for the sigma r theta stress. So just be careful. If you ever decided for some reason you wanted to figure out what's the actual stress distribution in this kind of plate with a circular hole and you wanted to use the solution they gave you, it's actually wrong. So don't use that solution. Thankfully, none of the homework assignments or anything that we're doing depend on that particular expression. So you don't have to worry about it, but it is still worth noting that that's a small error. It can be used in any situation. And in fact, the Mitchell solution applies to any plane stress problem. It applies even to the problem of that kind of like concentrated load problem as well. The solution ends up being a subset of, this collection of functional forms for the area stress function.
So if it wasn't a hole and the geometry was like something like a crank.
Right, yeah. The way that they typically do this, and I think the book even presents this particular solution, there's a way to do it such that instead of considering a hole, like a circular hole, they treat it as sort of like an ellipse. And then you can kind of consider the special case of what happens when the ellipse has like one principal diameter shrink to 0. So it's kind of like you have a straight crack through the medium. And that's how they come up with the solutions, still in polar coordinate form and still kind of assuming the Mitchell solution, but which give you these kind of like, small crack in an infinite medium. So kind of useful, kind of cool. All right. But otherwise, that's the Mitchell solution. That's kind of the solution for this plate with the hole problem. And what does it look like? If we were to now, given this distribution of stresses that we've computed using the Mitchell solution, the general solution to these plane stress elasticity problems, we solved all the boundary conditions. Now we get a stress distribution that looks kind of like this. And just, take a moment to stare at it. And then you tell me, what are some interesting features that you notice about the distribution of stresses that would happen in this plate? Sigma xx, the stress in this direction, sigma yy, stress in that direction, and then the shear stress. In XX, the colors are a little deceiving. And especially if you're in the back or, looking at what's here on the projected screen, it's kind of hard to tell, like, what's this color? But I'll kind of give it away. It's actually equal to 1. And I've defined the boundary conditions such that I've normalized everything with respect to sigma 0 being equal to 1. So it's kind of like I'm saying that if my stress achieves a value of 1, as displayed on these color plots, it basically means that it's actually equal to sigma naught, or basically the far field uniaxial tension stress that I'm applying to this plate.
So this 3 sigma 0 that you showed us in the previous picture.
Yeah. Basically, it's already illustrating more or less what the stress distribution should look like. If you were to consider in profile what the stress distribution looks like along maybe this kind of line segment. Far enough away from the hole, you would expect, that value of stress in the axial XX direction to be roughly proportional to sigma naught, the average stress applied to the boundaries of the plate. But as you get closer and closer to the edges of the hole, it starts to increase. It doesn't go to infinity. It does not become infinite, but it does become larger than the average stress. And in fact, in this particular solution, it happens to achieve a value quite fortuitously that's just proportional to 3 times that average axial stress. So that's precisely what we see, at least when we're looking at the axial stress. We could kind of do that same kind of cut through and look at what happens, up here, it's pretty much close to sigma naught. And then as you go down, it starts to increase up to a positive value, blue being more and more positive. So right at the edge of this hole, you see that the maximum stress is reached, which is roughly proportional to 3 times sigma naught. And same thing going on the other direction. It's also interesting to take a look at what's happening here for the YY stress. It's not just that the plate is subjected to only axial stress now. When you introduce this hole, you also generate other localized components of stress in both the Y direction and shear components of stress. And what's interesting is that while, these areas of the hole on the top and bottom faces of the hole are going to experience larger axial stresses local to the edges, in the case of the Y stress, far away from the hole, the YY stress it just goes off to 0. So green being kind of like the normalized value of 0. So anywhere you see kind of like neutral green, there's 0 vertical stress. But as you get closer and closer to the hole, it's kind of like the opposite thing. But rather than becoming a positive tensile value, it's actually compressive. So red here indicates that actually there's a compressive stress that gets generated in the vertical direction at the edges of the hole. So the hole is kind of doing something that looks like this. If it started out perfectly circular, then really what's going to happen is it's going to stretch out and kind of compress almost. So it's going to elongate this way, and it's also going to shrink. And in doing so, it generates compressive stresses at these edges of the holes and tensile stresses at the top and bottom edges. So visually speaking, that's kind of what it would look like. But the idea is this. Now that we know that local to the hole, near the edges, you're going to have stresses that start to get really, really big, or at least bigger than the average stress. And we can measure how much bigger those stresses become in a relative sense. So suppose I define something I'll call the nominal stress, which is really the average stress, or it's the stress that would occur in this plate far away from this local feature. So if you like, you could think of it as the net force applied to some boundary of the plate divided by the total area on the boundary of that plate. So it's sort of like the average stress. That's the nominal stress. And we can also measure what's the maximum stress that occurs for this particular solution of a plate with a hole. In this case, it ends up being 3 times that sigma naught value, or 3 times the average stress. We can now define something called a stress concentration factor. Who's here has heard of a stress concentration factor before now? Maybe, maybe not. Okay. Well, a stress concentration factor is really quite a useful tool, because at the end of the day, if all you really care about is not finding the solution to these complicated elasticity problems, which can be very time consuming and gives you a lot of information, it gives you full descriptions of what the stresses look like surrounding the hole. But at the end of the day, you probably don't care about all that. At the end of the day, as much as I want you to care about it, you probably just want to say, how do I design this? Or how do I choose, like whether or not to put a hole here? For that, you really just need to know, well, what's the maximum stress that would occur if I were to drill this hole? And to do that, really all you need to know is, well, if I can figure out what's the average stress that would otherwise occur in this plate if there was no hole, and if I know that, if I were to go through the trouble of finding these elasticity solutions, I could figure out what this maximum stress is. And then I could just figure out in a relative sense, how much bigger that stress would be, the maximum stress, relative to the average stress. And that's encapsulated precisely through this stress concentration factor. What's remarkable about this is that, at least if you assume the plate is really, really big, then the size of the hole isn't so much relevant. And the proportionality between sigma max and sigma nom is basically independent of that aspect of the geometry. So you can encapsulate this very general result and apply it to any number of different circumstances. Anytime you have a large plate with a small hole going through it, the local stresses surrounding the hole will achieve a value that is 3 times greater than the average stress. And the stress concentration factor just serves as the ratio of that maximum to average stress values. So assuming you have, let's say somebody came to you and said, for this particular geometry, maybe it's not just a hole, maybe it's I don't know, maybe it's a crack, or maybe it's some kind of square or something like that. Some clever person could go through the trouble of finding the elasticity solution, figuring out what the stress distribution looks like, figuring out what's the ratio of the maximum stress to the nominal stress, and then they just give you this one number, the stress concentration factor. And maybe they even plotted or parameterized it in terms of other geometric features. And if you as an engineer just wanted to say, well, I want to know how much bigger the stress is going to be here, all you need to know is the stress concentration factor. Everything else is kind of irrelevant. So people have done this. People have come up with these charts for different types of geometries and different types of loading. If you look in the appendix D of the textbook has a bunch of these charts, and they're actually quite useful. You might want to consider just hanging on to these for future reference, or at least knowing that they exist is kind of a useful thing at the very least. So for a bunch of different geometries and a bunch of different loadings, we can figure out what is this stress concentration factor, and we can use it then to estimate what's the resulting maximum stress that would occur somewhere in the plate. We actually don't know exactly where the maximum stress would occur, just knowing the stress concentration factor. But we can know that if we have material constraints that we want to impose, that the maximum stress can't exceed some value, all we need to know is the average stress, which we can reasonably estimate just using force divided by area, and the stress concentration factor, something somebody else came up with, put into some nice tables, and we can use directly. There's a homework problem that asks you to figure out what's the maximum stress that would occur in this kind of like elongated plate-like thing. And it seems like, oh no, I have to solve an elasticity problem. It's so complicated, but really they're asking you to just pick off values from this chart to determine what's the stress concentration factor for that particular geometry. And then very easily you can figure out then what's the maximum stress. So deceptively simple, but very useful. Yeah.
So I don't have like an average stress. I have a bending stress.
I think there are specialized solutions that include, like, instead of purely tensile loads, they also include other types of force resultants like torque or bending stresses. So in those cases, you could use maybe even superposition. If there's some combination of loading under axial and bending and twisting, you could superimpose that solution and figure out then what's the resulting maximum stress combining all those things. So possibly quite useful. But yeah, things to keep in mind. In any case, yeah, the homework problem on this should be relatively straightforward to do. Hopefully gives you some confidence. All right. Now, there's an interesting thing I want to point out, and we talked about it last lecture, this notion of Saint Venant's principle. It's the idea that if I have elasticity solutions that maybe include, I don't know, very localized forces like a point load applied to the boundary of some domain, it turns out that while this kind of concentrated load, local to the point of application of the load, will result in nearly infinite stresses in the local vicinity, if I move further and further away from this point, the stresses start to spread out. They start to equilibrate. And you can kind of think of what happens for maybe this kind of plate that has a characteristic width b. Maybe at some distance b/4 away from that surface where you're applying some concentrated load, the distribution of stresses might involve some localized stress immediately underneath that point. But as you move further and further away, for example, a distance b over 2, or, a whole value of b away from that load, things start to homogenize out. And that applies, obviously, in the case of that plate problem with a hole. As we move further and further away from the hole, the influence of the hole on the stress field kind of starts to be smeared out and becomes a little less relevant for understanding what's going on. But also, that same concept applies to understanding what's going on inside of long prismatic members, where in general, this width b might be relatively small compared to the overall length of the member. So if we want to know what's the stress distribution, maybe somewhere along the inside of this beam, far away from its supports, or however it's constrained or pinned at its ends, then to understand the internal stress distribution in this beam, if we don't really care about what's happening at the ends, then we can apply this St. Venant's principle, which really says that if you move close to, one or two principal widths b away from the point of application of the load, then it doesn't really matter whether you're applying a point load, whether you're distributing it over the edge, however you're applying it, it doesn't really matter. Because those influences really only affect what's happening locally in the vicinity of that applied load. But then a couple of diameters away, it basically all looks the same. So you don't really have to care about that. If all you really care about is what's happening kind of on average throughout the interior of these long, slender problems. So very useful principle. It enables us to do a lot of useful engineering design of beams and other kinds of long, slender members by assuming that the stress state interior to the member is going to look basically the same, and it's going to be relatively well distributed, with like a typical linear distribution of bending stresses and other kinds of things, regardless of how you're loading the ends. Now, it doesn't mean that what's happening at the ends is irrelevant. In fact, sometimes that's where all the action is. And in fact, that's if you were going to try to design, let's say, how to support the ends of this member or how to connect it to the rest of the structure, that's kind of where you would need to really dive into the details of these elasticity solutions and figure out how should I detail these connections so that I'm not achieving like localized states of stress that might lead to material failure. So if you care about that, if you're kind of doing the detailing yourself, you would really need to figure out, well, what is the actual stress distribution local to those portions of the boundary of these long, slender members. However, as is most commonly the case in engineering practice, a lot of people spend a lot of time establishing, good best practices for what standardized connections in structures should look like, such that all those considerations are kind of obviated. And it makes it such that you can kind of guarantee that as long as you're using a specified kind of standardized set of connections, you can kind of guarantee that the member is not going to fail at the connection location. It's probably, if it is going to fail, then it would have to fail somewhere along the length. If you're designing the connection, you got to do the work yourself, though. So it depends on what you want to do and kind of what you're asked to do. But yeah. All right. So yeah, go ahead.
In the case of the overflow, can we have like a rough estimate
of like, what would be the magnitude of this kind of maximum stress, assuming B over 4? Well, in that case, we could refer to our elasticity solutions and figure out, like what would it need to be? There's probably a way to do it just given the solution that we derived previously. But the idea is, you could figure out, given this radial distance or this kind of vertical distance, there's sort of like a die-off. It's going to look like 1 over r, or 1 over, this axial coordinate. So it's going to decrease proportionally from infinite. It's going to be infinite right here, but eventually it'll kind of die off, and it'll be proportional to that. So that's kind of one way you can do it. But in general, you would still need to know what's the functional form of that stress distribution, given the solution obtained from, the previous stuff we presented here. So it can be done, but requires a little extra work. Yeah. Okay. So now that we've covered everything related to concentrated loads in this setting, I want you to kind of reflect on the fact that this scenario of having a concentrated distributed load, really it's a distributed load per unit width. Again, if we're talking about an infinite plate, the plate technically has a finite width, and this distributed load, or rather concentrated load, is distributed over this kind of like finite width. Even so, we get a practically infinite distribution of stress, and it depends again on this kind of 1/r thing. You probably could figure out, what's a reasonable way to estimate what's the max stress as you continue to go down. But this would give you a reasonable way to do that. Now, in practice, that's never really what the stress distribution will look like. In practice, you'll never have a truly concentrated load applied to a boundary. And it has to do with the fact that, well, how would you truly actually apply some concentrated load? You could think of like a knife's edge or like a wedge or something, pressing down like the tip of a cone or something into some infinite elastic medium on its edge. And maybe that way you could try to emulate the behavior of some kind of localized force. But in general, let's say if you had like a tire on a roadway, or maybe like in the case of one of the homework problems, the wheel of some railroad car applied to some, railroad rail, or any kind of situation where you have an object that has some local curvature that could be idealized as being kind of round or spherical, and maybe some other object that it's coming into contact with. In general, those two objects, neither of them is strictly rigid. They're both kind of elastic. There's no such thing as a truly rigid body. Every body is kind of elasticy and kind of bounces when you kind of compress them together. So what happens if we take this, I don't know, let's say sphere, and we press it into this kind of surface that has this kind of exterior edge? What'll happen is both the sphere and this kind of infinite medium will compress against each other, and they'll deform such that some collection of points will be shared between them. They'll come into contact. So rather than being just a single point at which these two objects contact, they will deform relative to each other, and the stress that gets transferred between these two objects won't be at a singular point, but will be distributed over some finite area that might have, in the case of a spherical particle, kind of sitting on some infinite elastic medium, might have some characteristic width or radius A. In that case, we might want to know, well, if the stress is not really acting at a single point, if instead it looks more like a distributed pressure load over this small circular area that might form between those two bodies coming into contact, what does this distribution of pressure, distributed force, look like in the vicinity of this kind of area of contact? This is precisely the question that was answered by this guy, Hertz, long time ago. And if you recognize the name Hertz, well, hopefully it doesn't hurt you to think about it. But Hertz is the same guy that came up with a lot of different things in electromagnetism. He's the same guy who the unit Hertz for frequency is named after. Same guy also came up with the solution to this particular elasticity problem for two spheres coming into contact, and a bunch of other kind of related problems. So rather than idealizing things as a sphere sitting on like a flat plane, think about it in terms of two spheres coming into contact might have different radii and might have different elastic properties. So sphere 1 might have elastic modulus 1 and radius 1, whereas sphere 2 has elastic modulus 2 and radius 2. Okay. If those two spheres come into contact, they will deform relative to one another, and in between them, they will form a continuous area of contact that will look kind of like a local circle. So this circle, this circular area of contact, will have some distribution of stress over that finite circular area that looks kind of like this. It'll look like a bubble. Near the edges of this contact area, the local contact pressure should be 0. It should be 0 because really, if we say that any points not in contact between these two spheres, certainly can't have any stress acting on their boundaries. It's only once they start to come into contact that you go from 0 contact stress to now ramping up in contact stress. Then we really have to insist that at the boundaries of this contact domain, that the stress at those locations has to be 0. So it has to start from 0 along the boundary. But it'll ramp up and it'll bubble up to some kind of local maximum right at the center of this contact area. And we can kind of approximate what that maximum stress should look like by assuming that this bubble is going to take a form that looks kind of like this, that the distribution of pressure distributed over this area will kind of look like what is, at least in this description, I'll define it as a spheroid. It's kind of like a sphere, except, one of the axes of the sphere might be elongated. So if you think of this distribution of pressure as being kind of like a sphere that's been stretched in one direction, where the relative axes of that sphere are simply the radius of this contact area, and the other axis of the sphere, or spheroid, is equal to basically the magnitude of this maximum pressure, then really we can express then what is this maximum pressure, assuming this distribution of spheroidal contact stress by just simply integrating this assumed distribution of pressure over the contact area and equating it to whatever net contact force has to occur between these two bodies. Given that, we can integrate that and figure out what is the resulting maximum contact pressure between these two bodies. And it's not an infinite pressure anymore. It's a finite value, but we can measure it. And it turns out that because that maximum stress has to be equal to whatever stress is interior to either one of these two spheres, if we look a little bit below the surface near that point of contact, then really this maximum contact pressure also describes the maximum stress, vertical stress, acting in either one of these two spheres. Pretty cool. We can do some other things to then also figure out what is the apparent radius of this contact circular area. And it requires basically just applying some formulas and accounting for the fact that that radius or area of contact will depend partly on, how elastic these two bodies are. Their relative elasticity influences how much they'll deform relative to one another. We can also determine that expression for what's the relative area of contact depending on how big these two spheres are. Obviously, the bigger they are, then presumably the larger this contact area would become. And we have to kind of weight it in a relative sense depending on how big one is to another. So we can include all these different contributions. How big are the spheres? How stiff are the two spheres in terms of their elastic properties? And we can figure out what is this radius of contact. And it looks kind of like this. It's a fairly straightforward expression that depends on the applied load and the elastic properties and the size of the two spheres in contact. So pretty useful. If you want to estimate, given some idealization of two objects in terms of just spheres coming into contact, you can then figure out what is the actual maximum pressure that would occur at the point of contact. Very useful if you wanted to know, let's say, the pressure in a bridge deck immediately below the point of contact where you might have some wheel sitting on the top of a bridge deck. And you might ask, well, I have a solution in terms of spheres though. A wheel doesn't look like a sphere, and nor does the bridge deck. It's technically totally flat. You can specialize this same equation to those different scenarios just by kind of taking things like, well, if I wanted to represent the case of a sphere sitting on an infinite planar surface, I just take this radius and send it off to infinity. So it's kind of like a special case. You can just say, make this sphere really, 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 really big, and then it kind of looks like it's just a flat surface. And then you have a sphere sitting on basically an infinite medium. Kind of a cool trick. And you can specialize it to a bunch of different cases. But there's an even more general case, and this one is particularly relevant for solving the homework problem. It's the case where you have not just two spheres coming into contact, but potentially two ellipsoids coming into contact. And the book has a picture of this to try to describe it and explain it, but it's a little bit unclear. So hopefully I've cleaned up a lot of the imagery here. The way to think of it is that if you were to look at this scenario, this kind of assembly of two, spheroidal capped, bodies coming into contact at a single point, loaded through their center lines, then from a top-down perspective, you can imagine what this kind of thing, this top body will look like, and this body will look like. From a top-down perspective, they'll look kind of like ellipses. really these surfaces have some curvature such that, it's an ellipsoid, at the tip of each one of these two prisms, such that when they come into contact, they'll be contacting maybe along their center lines, but, they'll have these different, principal axes or radii of curvature. So this particular body might have radii of curvature that differ, R2 and R2 prime. Same thing, this one might have radii of curvature R1 and R1 prime. And if they're sitting on top of each other, they may not necessarily be aligned such that R1 and R2 are pointed in the same direction. They might actually be rotated relative to one another. So they're loading each other, still along this principal axis, but this one might be twisted a little bit. And that can be accounted for by introducing, let's say, a relative angle of rotation theta that measures the difference between R1 and R2, or equivalently R1 prime and R2 prime. Okay, that's fairly straightforward. What we want to know is, what is the resulting area of contact? What does it look like? And how do we get the resulting maximum contact pressure in this much more general case? It turns out the resulting contact area will look like an ellipse. Rather than just a circular contact area, it'll be ellipsoidal with principal axes or principal radii A and B. And in general, this ellipse won't necessarily be aligned with these principal axes of those two bodies coming into contact. It'll have its own distinct set of axes that might be pointing in different directions. But if we wanted to know what's the relative maximum contact pressure, assuming we knew what the pressure distribution looked like, assuming we knew what's the maximum force, and assuming we could characterize or measure what are these principal radii, A and B, well, we can do exactly the same thing, just integrate over this kind of assumed area, assuming now not just a spheroidal distribution of pressure, but rather an ellipsoidal distribution, slightly more general, but ends up being an equally simple expression for the maximum pressure. It just looks like this. So take the force, divide by area, and then also include a factor of 3/2. Fairly simple. Okay. Now, the resulting expressions, if you wanted to know what are the values of A and B, the resulting expressions for determining A and B, and subsequently to determine what's this maximum contact pressure, are quite a bit more complicated. In this most general case, it looks pretty nasty. But the main thing to conclude from all this is that in spite of the complexity, ultimately, it all just boils down to plugging in different dependencies on those different radii of curvature, including a dependence on the relative angle of rotation between those two bodies coming into contact, and also eventually boiling it down into solving a problem that looks kind of like figure out the equivalent radius of contact, assuming that you can approximate the solution by treating it not as an ellipse of contact, but as just a circle of contact. And you can boil it down into this format, where you're basically just figuring out what's the radius of that equivalent circle. And you can use the same exact formula as you did for the case of sphere-on-sphere contact. Looks pretty cool, but you have to modify it slightly. You actually have to include a correction factor. Even though you kind of go through all this process and you try to treat it as an equivalent sphere-on-sphere problem, you do still have to include this correction factor, which kind of depends on some intermediate parameters that you compute along the way. But once you have that, once you figure out the equivalent radius of this equivalent contact circle, then you can figure out the maximum pressure, no problem. Again, same equation as you did before. All right, fairly simple. And what's even better is that you can specialize this further, and it actually simplifies quite a bit. If, let's say, you had the case of not two ellipsoids coming into contact, but if you said maybe two cylinders coming into contact, two crossed cylinders, such that the relative angle between them is 90 degrees. So they're perpendicular to each other. And you want to know what's the contact area that would occur between these two cylinders sitting on top of each other. Should be an ellipse. We kind of know that from the general solution. And you can get this solution just by plugging in that one of these two principal radii of curvature of these two objects has to zoom off to infinity. That's how you specialize it to the case of cylinders. You would set R1 prime equals infinity, and same thing, R2 prime equals infinity. And that's how you would get a situation that kind of looks like this. It turns out this is basically equivalent to that homework problem where they're asking you to figure out what's the contact stress between, let's say, a railroad wheel, a cylinder in one direction, and a railroad rail, which is kind of roughly a cylinder in the opposite direction. So you can idealize those situations basically as cylinder on cylinder contact, plug it into those previous complicated expressions, and it boils down to something a little bit nicer. Now you just have to compute this intermediate term for an equivalent radius of curvature between these two objects. You still have to compute this correction factor thing. The book has some tables for how you would actually determine this. But if you prefer to use this formula, I think it might be easier to just use the formula. You can use this and then just plug it in and then you're good to go. So that's about it. Relatively straightforward to do. All right, I think we're out of time, but hopefully that gives you all the ammunition you need to complete the homework assignment, which I think we'll stick with the original deadline unless there's certain concerns about anything that we might not have gotten to. But otherwise, I'll see you all next Tuesday.